Okay, this is about improper integrals. So there's a couple of reasons why an integral might be called improper. Today I'm going to talk about having an infinity as one of the limits of integration. So let's suppose that f is continuous, just for the sake of sanity, I guess. If I have infinity as my upper limit of integration and a is just some number, then what I'm going to do is I'm going to basically replace infinity with t, and I just do the limit as t goes to infinity. And that's kind of the running theme for improper integrals, that there's like a little issue, and the issue is having infinity there, and instead of dealing with that, we replace the issue with a t, and we do the limit as t goes to whatever that was. So that's what we do here. Similarly, if I have negative infinity as my lower limit, then I'm going to replace that with t and do the limit as t goes to negative infinity. It's also possible that I have negative infinity and positive infinity as my limits of integration. And then I can just break it up into two parts. Like I'll go from negative infinity all the way to some number that I choose. This could be anything. Often we just choose 0 out of convenience, but it could really be anything. And that covers everything from minus infinity all the way up to a. And then separately I can cover starting at a and going all the way to infinity. And then that between the two, that covers everything all the way from minus infinity to plus infinity. And of course, this one I would evaluate this way, and this one I would evaluate this way. So we know how to do both of these. Okay, so let's do something. Say I have the integral from 1 to infinity of 1 over x squared. And the question is, does the integral converge? And what I mean by that is having a finite value, because of course, when I evaluate these, there's always a limit involved, and this limit might not exist, or it might be infinity or negative infinity or something. So that's what I mean by have a finite value. It really might not have a finite value. If it doesn't, then we say it diverges. So that's the question. Does the integral converge or diverge? If it converges, find the value. So this thing, let me preemptively write x to the minus 2, because that's often a good move. So what is my issue? I have infinity up here, so let me replace it with a t and do the limit as t goes to infinity. So I'm there, and this is an easy thing to find the antiderivative of. So I increase the power by 1, and then I divide by that new power. And I do that from 1 to t. Okay, here I go. Okay, what's happening? This is just a negative 1, so I'll just write a negative sign there. So t to the minus 1, here, because this negative sign distributes. So t to the minus 1 minus 1 to the minus 1, which is just 1, of course. And okay, as t goes to infinity, this is 1 over t, so this goes to 0. And this is just 1. So I got 1. So answering the question, it did have a finite value of a 1. So one way of saying my answer is it converges to 1. All right, let's do another one. This one's going to be pretty similar but different. So I'll try to make this go fast, and it's the same instructions. We're just going to say it converges and whatever the value is, or if it doesn't have a finite value, we'll say it diverges. All right. So what do we do? I have infinity as my limit of integration, so I'm going to replace it with a t and do a limit as t goes to infinity. Let me write x to the minus 1/2 here, because I'm about to integrate this thing. Okay, this antiderivative, I increase the power by 1, so now it's positive 1/2, and then I put the reciprocal of that in front, and I do that from 1 to t. Okay, here I go. So I've got this 2, and then I'm going to have a t to the 1/2 minus 1 to the 1/2, which is just 1. All right, so now I look at this. As t goes to infinity, t to the 1/2, that's the square root of t. So roughly speaking, square root of infinity is infinity. If I do the square root of a very large number, I get a very large number. So this limit is infinity. So we just say this diverges. That's okay. That's a possible answer. Okay. Let's do a slightly more involved one. So integral from negative infinity to 0 of x times e to the x. So, and it's the same instructions for all of these. So we'll say it converges or diverges, and if it converges, we'll say the value. So this time the issue is negative infinity, so I'll do the limit as t goes to negative infinity. Integral from t to 0, x e to the x dx. Okay, so in the examples we've done so far, we were able to find this antiderivative with no problem, but now I have a slight issue. But that's okay, we've learned techniques of integration. In particular, this looks like maybe integration by parts. So maybe let me kind of go off to the side just to work on this antiderivative. So I took off the limits of integration, I took off the limit, I'm just going to do this antiderivative. And like I said, this looks like integration by parts. So I don't see any logs, I don't see any inverse trig, I do see a power of x, and that's just this x. So I'll make that u. dv is the rest. du is dx. V is the antiderivative of e to the x, which is just e to the x. And so this turns into u times v minus the integral of v du. So we're there. Now we have to do this integral, but that's easy. So I'm there. And I'm not going to bother writing plus c because I remember that this is, I'm just going to put in limits of integration, and there's no point of writing plus c in this case. So I'm ready to go back to the big picture again. So I've got the limit as t goes to negative infinity of, okay, it's going to be this thing. T and then 0. All right, we plug these numbers in. Okay, so I put in 0, this is going to be 0, e to the 0 is 1. So that's me plugging in 0. Now here's me plugging in t. So I got that. Let me clean it up just a little bit. Okay, I've got a -1 minus t e to the t plus e to the t. All right, so what am I looking at now? All I have to do is this limit, and I can do these three things separately. This is just -1. There's nothing really to do there. This is, well, t's going to -infinity. E to the t, draw this picture again. This is my mental picture, y equals e to the x. But t is going to -infinity, so it's like I'm doing e to the -infinity. So it's basically 0. It's this horizontal asymptote. So what we're looking at here is an infinity times 0 form. So that's going to take us a little bit of work. But let me keep moving because I was sort of taking inventory. This gave us no problem. It's just -1. This one is going to give us a little bit of problem. This one's just 0. The e to the -infinity, that's just 0. So that's not going to give us a problem. So let's work out this one. So let's forget about the big picture for the time being, once again, and just talk about the issue, which is the limit as t goes to -infinity. I'll skip this part. I'll just write this part. So like we said, this is an infinity times 0 form. And what do we do with those? We stick something on the bottom. I am going to prefer to keep my t on the top, because when I do the derivative of that, it's just going to be 1. And then I'll write e to the -t on the bottom. So this is now, so the top's going to -infinity. The bottom, this would now be e to the positive infinity, because t is going to -infinity, and that's a -t. So e to the positive infinity, that's like, I'm looking at this graph again, but I'm looking at the part far to the right. So this is an infinity over infinity form. So we're justified using L'Hopital's rule. Derivative of the top is 1. Derivative of the bottom is using the chain rule, e to the -t times -1, because that's the derivative of the inside. And that's, yeah, let me clean this up. I've got a negative sign from here, and then e to the -t on the bottom is just like an e to the t. And so now I look at this. This is my new limit. T is going to -infinity, and I've got e to the t here, so I'm looking back at this graph, but it's the left part again. So this is 0. Okay, we take a step back. We remember the big picture. I was doing this integral. We worked it down to here. We were comfortable with everything except for this one part, but now we just figured that out. So the original integral is I've got a -1 here, minus whatever became of this, which we just figured out was 0, plus this, which we knew was 0 a while ago. So I get -1 out of that. So we answer the question by saying it converges to -1. All right.